Okay, let's start the second day for the major awards speech. The first speaker would be Professor Mori from Japan. I've known Professor Mori for 50 years, since I met him first time in Harvard University. He's one of the most impressive mathematicians I've ever met, brilliant, and has created a subject in algebraic geometry, a very major part of mathematics. Algebraic geometry is always the core of mathematics, reaching from geometry, algebra, and mathematical physics, representative theory, and almost every subject in mathematics are related to algebraic geometry. I'm very pleased to see its rigorous development in the last 50 years. A major branch was created by Professor Mori. And so he's going to talk about from Hartshorne conjecture to birational geometry. Thank you.
Thank you very much, Professor Yao. I think you flattered me too much, but anyway, let me start. Okay, so with this title, From the Hartshorne Conjecture to the Minimal Model Program, I'd like to give a personal review of my mathematics. So, okay. So it consists of two parts. The first part is before 1975, when I was a student at Kyoto University. And then the second part is after 1975, when I became a research associate in Kyoto University. Okay. Well, so I don't know the audience, so let me start with the sort of trivial things. So algebraic variety is a solution, the set of all the solution of a set of equations. And when the equation has only integer coefficients, for instance, we can plug in complex numbers, or real numbers, or integers, or rational numbers, various situations. So depending on the situation, what I mean by solution may change, but it's not that serious. And the projective space is sort of a very typical object next to affine space. It's patched by affine spaces. And projective space contains points at infinity. Okay, so it's a just sorry. So it consists of solutions of some polynomial equations. And algebraic variety you may remove some closed subset, but let's not worry about it. So one intention of algebraic geometry is to classify them, the solutions. But the meaning is not clear. So we mean that to classify them up to change of birational change of variables or coordinates. So typical example is a graph, x2 equals g of x1, and it's birational to a1, of course, because by projection you get the birational map. And the circle. So when I was a high school student, I used to use this kind of diagram, this kind of picture, and circle x squared plus y squared equals 1 is parameterized by t, one variable t in a form like this. And by rational curve, I mean a curve with a rational parameterization in one variable. So we will use this notion. Okay, so algebraic varieties start with curves, that is dimension 1. And so C, by adding points at infinity, a curve will look like this. So the simplest is P1, or Riemann sphere. Sorry, I'm talking about complex solutions. And G equals 1, the elliptic curve. And for higher genus, it has many more handles. So G, genus of C, is the number of handles of C. And if you look at it more closely using differential geometric notions. So at each point, sphere always look like this, curved on one direction. G equals 1 elliptic curve may look like curving, but you can flatten it. And for G bigger than 1, it looks like a saddle, curving downward in one direction and curving upwards. So positively 0 or negatively. So these are the local picture at each point. Oops. And this is done in the 19th century by Riemann. And in the surface case, the situation is different. So given a surface S and point P, smooth point, you can sort of do the process, something called blowing up. That is to remove this point P and put back the rational curve called -1 curve in there. So S removed point P and added a curve C, sort of expanded. So this is a blowing up, and going down, this is a contraction of C. And Enriquez Kodari classification intends to generalize the classification of curves of the previous page, 2-dimension 2. In this case, up to blowing ups and downs or contractions. And this was based on the minimal model program in dimension 2. And it was done around 1900 by Italian school. So this is before 1975. So I'm talking about the conventional minimal model program. So if you are given a projective surface, and if you can find the -1 curve, you contract it to something smaller. A curve is replaced by a point, so it gets smaller. And you repeat this until you cannot find any -1 curve. Then the result, X, is either a P1 bundle over a curve. In real picture, it looks, the real solution looks like this. A curve and above it a line over each point, or P2. So this corresponds to G equals genus 0 curve, P1. Then minimal model X min, which corresponds to G bigger than 0 curve. Those days, the result looks beautiful, but the argument is quite complicated. It was based on the case division. And so this was the status of MMP as far as I understood those days. And of course, people try to generalize it to dimension 3. But there are various difficulties. So on a threefold, if you consider the analog of blowing down, you either blow down a device surface to a point or a curve. Blowing down to point is maybe easier, but blowing down to curves was a headache. So if we contrast the surface S on a threefold to a curve, so on X, surface S is replaced by a curve. So this is like a P1 bundle. S to C is like a P1 bundle in the previous slide. Okay, so far it looks okay. But starting with a projective threefold X, dimension 3 projective variety, the blowing down, the variety Y, can be non-projective even if X was a projective variety. Okay, but let's try with non-projective variety. But then Y can be even non-algebraic, even if X is an algebraic variety. So it goes out of the categories. And if it's a non-algebraic analytic variety, I don't know how to proceed. Okay, that's the situation as far as I understood. And there are some of the activities those days. So originally, people sort of hoped or expected birational morphism to be a composition of simple blowing ups of a point or a curve. But Hironaka's example in 1962, if I remember right, said that it's impossible. It says a birational morphism of threefolds, which is not a composition of standard blow-ups in dimension 3. I will show you a picture later. And then, since reaching a minimum model seemed hopeless, alternative was that classification of algebraic variety without minimal models. This was a project by Itaka. And also, Ueno gave examples of threefolds which cannot have a smooth minimal model, whatever it means. Okay, so this is Hironaka's example in 1962. So start with a smooth projective variety with smooth three smooth curves meeting transversely at one point. Then one can blow up, meaning removing these three, you can put back these four surfaces in the middle of P2 and somehow paste it like this. So if you look at this, how to reach this by sort of contractions. Well, first choice is this P2, contracting P2. But if you contract this P2, you get a singular point. And so if you avoid it, there is no other way, because these do not look like a standard blow-up of curve. Okay, so in this sense, it was not decomposable into blow-ups along smooth curves of points. Okay, so these are the status in 1975. And in 1975, I became a research associate, and I started as a researcher. Okay, so let's come back to the question of how a variety is carved. So I'm using differential geometry, which I'm not good at, but let's try. Okay, so given an algebraic variety and given a point P, and in the tangent space, you pick up any any real plane. And on the plane, in each plane, you pick up a direction and you consider geodesics around there. And you change move the directions, all the directions on this P2, you get some sort of a surface. And as we saw earlier in the Riemann surface case, either it's curved positively, negatively, or zero. And the reason why I marked this is when I was a third-year student, I took a seminar, and the tutor, Professor Sumihiro, was actively interested in this kind of phenomenon. And the question is, what if a variety is positively curved everywhere for all P and for all directions, P2, for R2 in the tangent space of P. Okay. And this was a statement of the Frankel conjecture. So if a K1 manifold is positively curved at every point P and R2 in the tangent space, then X is isomorphic to a projective space, Pn. But this is not the problem I was working on, or he was working on. He was working on algebra geometric analog, and with a slightly weaker hypothesis. So Hartshorne made a conjecture in 1970. Around this time, he was visiting Kyoto, and he used to make lots of conjectures. And somehow, out of this statement, he came up with this one. So every projective manifold with ample tangent boundaries isomorphic to a projective space. So the point is this positively curvedness at every point P and R2 implies ampleness of the tangent boundary. Okay, so these are the subjects surrounded me those days. So minimal model program, dimension 2, and Frankel or Hartshorne conjecture, Sumihiro was interested in. And biregular classification of smooth final threefolds. So when I was a master course student, I was interested in the final threefolds. I'm not going into this. Okay. So this is a sort of more general project, and this is about a very special variety. And Hartshorne conjecture. So those days, this is the problem of Sumihiro's, not mine. And one day, I think in 1975 or so, Mabuchi, a friend of mine, he was studying Berkeley. He sent us a preprint of his thesis. He showed that using a Riemann formula, Frankel conjecture, assumption of Frankel conjecture implies that automorphism group is positive dimensional when dimension is 3. And then I got interested in, and one day I found something one day, and I went to Sumihiro's place, and we discussed till morning. And we managed to improve this a little bit. But the method does not generalize to dimension bigger than 3, because this hypothesis, automorphism group bigger than 0, is just impossible to settle. But then I stayed at Harvard University as an assistant professor from 1977 to 80. That's where I met Professor Yao. Okay, so when I arrived at Harvard, I sort of forget about this since it's out of reach. Okay, so this is a copy of the previous one. Okay, now I gave a slightly weaker aspect. So given a curve C, the average of the curvature I mentioned sort of earlier, for each point P and R2, I get curvature, the Gaussian curvature, and by moving P and R2 in the curve C, I can get average, which is some absolute constant times the intersection number of minus k times c. Minus k is the anti-canonical divisor. So this is a purely algebra geometric notion. With curvature, it is not. I mean, of course, I use it to talk to people, but I really don't use it. So this is really my field. And you see, this way is more likely to happen. And this is very special. Sorry, let me. So there are various notions of being positively curved. Because so the top is the strongest and bottom is the weakest. So sectional curvature is positive for P and R2 in the tangent space. The assumption I mentioned as Frankel conjecture. And the tangent bundle being ample, the Hartshorne conjecture. And the anti-canonical bundle is ample, which is the definition of X being Fano. So minus k is the determinant bundle of Tx. So if tangent bundle is ample, of course, minus k is ample. And the intersection number of minus k, that's C, is positive for curve C in X. Of course, this is implied by the above because being ample, minus k intersects is every curve positively. So these are the sort of positively curvedness notions. And so at Harvard, I somehow managed to prove Hartshorne conjecture as a corollary to the following. If a projective manifold is positively curved along a curve C, that means minus k times C is positive for some curve C, then X contains a rational curve. So this may look like a very naive statement, but with this kind of general hypothesis, there are not this kind of existence theorem. It is not known to me. Okay, and so this was the Hartshorne conjecture or Frankel conjecture are problems in characteristic zero, or mostly complex numbers. But I could prove this only by characteristic P argument. I will mention a little bit later. And the reason of characteristic P is I can use Frobenius morphism, P's power morphism. And so essentially the proof of this known only in characteristic P. So it would be nice to have a characteristic zero proof. Or if you are successful, you may generalize it to a Kähler manifold or something more. Okay, so finding a rational curve via characteristic P. How do I do that? So this is the illustration I borrowed from a famous red book by Mumford. So this is spec Z ring of integers. It consists of points. It consists of prime numbers, and 0 is also. And above each prime, there is a algebraic geometry in that characteristic. So for instance, in characteristic 5, there are 1, 2, 3, 4, and infinity. And generic point. And if you pick up a point in characteristic 0, like root minus 1, it has various reductions. In modulo 2, square root minus 1 is 1. And modulo 3, it does not have an immediate root solution. So you have to go up to higher, but in characteristic 5, 2 and 3 are the roots. And so given a point, you get sort of a trace, its trace all over the primes. And the way I proved existence of rational curve is given algebraic variety, look at all the coefficients and coefficients of the polynomial, and there are only a finite number of them, and I list them, and if I remove some prime numbers, I can arrange them, and so that I can extend the variety over some sort of scheme. So starting with the algebraic variety of a complex number, somehow I put it in this scheme, and in most primes, it has some sort of reduction. And for each prime, I find a rational curve. And by bounding degree for almost all curves, somehow I get the lifting to characteristic 0. Maybe it's easier if you see the proof. But and you see, my proof requires this scheme. Without it, I cannot prove it. So it's a very strange feeling. Okay, so outcome of rational curve. In the search of applications. So once I get the rational curve, proving the Hartshorne conjecture wasn't that difficult. Given a point, and you consider all the points given a point, you consider all the minimal degree rational curves. So it's like on the projective space, pick a point, and around all the P1s, lines through it form P minus 1, one dimension less. And you prove it. And then once you have the moving family of lines parameterized by P1, Pn minus 1, you sort of recover the whole Pn by sort of geometric arguments. So that's what I did. And, but you see, I did not use the assumption of positive curvedness that much. And that's why I get curious. So this is this curiosity of mine was the starting point of everything. Okay, so Frankel-Hartshorne conjecture. I could solve it in the Hartshorne conjecture in 1979, and the Frankel conjecture. Well, my method was totally algebraic and characteristic P, and I believe differential geometers are very much annoyed, and Su and Yao immediately settled it by proving the Frankel conjecture. But anyway, so this was the starting point of my curiosity. Then in a moment I will explain what extremal rays is, but this is the first outcome of my curiosity. And from there are two directions. And first, the classification of final threefolds. I couldn't do this with Mukai. Well, to be frank, he did most of the work, so I should feel guilty. But anyway, and then I started working on the minimal model program. Okay, so the idea is how to find the key structure of curve along which the variety is curved positively. So the behind this is Kleiman's cone of curves, or Hironaka-Kleiman's cone. It's a cone in the H2 with coefficients R. So each curve C in X has a homology class, and H2, H lower 2 is a finite dimensional vector space, and in there you have each curve C has a vector, and you consider all the classes C bracket of C, and consider the cone generated by them, or you consider the closure. I don't take it that serious, but okay. And K or minus K has takes a form of a function, linear function, since C times K has a self-intersection number. So on this space of H2, K appears as a hyperplane, and the center is the hyperplane K equals 0, and the left side K negative and the right side K positive. And this is an invariant. And let L be an ample line bundle, and then L is positive on the closure of Cx minus origin. And the plane L equals 1 looks really like this, away from the origin. Okay, so one day, no, the other day, I was in a discussion of whether mathematics is pure logic or not. And mathematician says it is not pure logic, and no mathematician says, yeah, they are. So I use this picture to remind that it's not a pure logic. Okay, so when I given an algebraic variety, I try to sort of visualize it or draw something on a canvas, not a physical canvas. But so this is a canvas to draw an invariant. And so being a geometer, I'm sort of entitled to use pictures. And every mathematician uses some kind of invariant, but we are closer to using pictures. So invariants are similar to abstract paintings, unlike art, because art is very special. Each person draws a totally different picture. If everyone draws the same picture, it's not art. But in science, it needs objectivity and reproductivity. But still, it's like art. And invariant is defined for each figure. And I should also mention that about this abstract painting. So differential geometer, they have many more notions on the studying local situation, like Gaussian curvature. So they can draw very concrete paintings, but algebraic geometers don't. So we have to draw abstract painting. That's what I mean by the abstract painting. So this corresponds to algebraic geometry corresponds to cubism in painting. So I hope this is not against copyright. So I went to exhibition of Paul Klee, and I was interested in his words. Art does not reproduce what one can see, but makes seeable what one cannot see. And you see, you can replace this art by science. Okay, so I like this word. And this is supposed to be a steerable grandfather, and you can you can find the meaning out of the triangle or circle, whatever. Okay, so having looked at this, we go to extremal ray. So Cx bar, the closure of the cone, is locally finitely generated in half space K negative, this side. So it looks like you have something, not circular. So each ridge line on this side is called extremal ray. And to be slightly more precise, if you keep away from the right side, there are only finite number of vertices. And together with these finite number of vertices, they span this cone. And the necessary vertices generate extremal rays. And it's natural to ask, what's the geometric meaning of each extremal ray? So going back to the surface case, so we pick up an extremal ray. And there are three kinds. P2 type, so it's P2, nothing more. It's pure bundle over some curve. And fiber, class of fibers belongs to R, the extremal ray R. And birational type, there is a -1 curve, and its class is in R. So in this case, in the first case, P2 type, P2 is mapped to a point. Every curve belongs to R. And pure bundle type, every curve collapsed by this bundle structure is a member of R. And the birational type, -1 curve belonging to R is collapsed to a smooth point. So this is the geometric meaning of R. So a curve C is sent to a point P below if and only if the class of C belongs to R. Okay? This is the contraction morphism of R. Okay, so going back to the minimal model program. So if a smooth projective surface has an extremal ray of birational type, we pass to its contraction, X prime, and work on X prime. And we repeat it until there is no extremal ray of birational type. Then there are three kinds. P1 bundle, or P2, or minimal model. So this reproves two-dimensional case. And with this setup, it can also imply the equivariant MMP. If you have a symmetry of group action, it automatically is compatible. And X is a minimal model here if KXC is non-negative for C. And K being net. 3, you need another thing, singularity. So it was provided by Miles-Reed as terminal singularity. So if I start MMP from a smooth n-fold, n bigger than 2, and can get projective space of n-1 dimension, and that is mapped to a singular point. So it's very likely to happen. Then it's not smooth, and you have to allow singularities. And once you allow singularity, you have to reprove the Kohn theorem for varieties with that kind of singularity. And so you have to reprove this. And if you do it, you may again get the worst singularity, that there is no end. And Reeves defined a class of singularity, terminal singularities, that exactly works for MMP. And with this framework, Kohn and singularity, Kamata, Reed, Shokroff, Benveniste, and others constructed the general framework. Okay, so in dimension 3, it goes like this. Funnel fibering corresponding to P2. So either funnel threefold being contracted to a point, or the repetitive surface bundle over a curve, or a conic bundle over a surface, no matter anyway. So 5 bars are funnel varieties. The important point is that this is the global structure of the threefold. And divisorial contraction. If it's not a global structure, it corresponds to birational contraction in the surface. And the first candidate is a divisorial contraction. Divisor surface is contracted to a point or a curve. We saw a bad example of this type earlier. And in this case, target is a good space, and it contracts a divisor. So target is maybe it has a singularity, terminal singularity, but the target is always projective. Then the third one, in dimension 2, this didn't happen. So this is a new phenomenon. It's a small contraction. It doesn't contract any divisor. It contracts a curve, irreducible or reducible. And the trouble is that the target image of this curve is a singular point. It's a bad singular point. And there you cannot talk about intersection number of k with a curve. So with the above two, we can sort of keep MMP going, but not the third one. Okay. So this is a situation we had trouble. So in this case, we need an operation called the flip. It's like a surgery. So we remove the curve, and we put another curve, not the same curve. It's a different curve. Since for the original contraction, minus k is ample, but after the replacement, the k is ample. The k has opposite sign. So we remove a subvariety of higher codimension and put back a subvariety of higher codimension. And this is supposed to have a nice property, like a nice singularity and so on. And flips do exist. In dimension 3, I managed to prove it in 1988. And for higher dimensions, Haycom-McCannon proved it in 2007 in all dimensions. This was done along with Shokroff's philosophy. So in dimension 3 or larger, we repeat divisorial contraction and flips. And if it terminates, we get the minimum model of nanofiber. So in dimension 3, Sokolov found a very nice invariant called difficulty. And by counting it, it easily terminates. And in higher dimension, the termination of flips remains the biggest problem. And but with a particular kind of MMP, something called MMP with scaling, it terminates in most cases in all dimensions. I don't specify what it means, but it's done by Birka, Cassini, Haycon, and McCann, 2010. And they obtained more general versions using relative version and log version, but I suppress them for simplicity of argument. Okay, so reviewing it, so in dimension 2 case, we keep contracting -1 curves until there is nothing, and we get P2, P1 bundle or minimal model. And dimension 3 case, it proved by these. And there are 3 new ingredients. We need an external ray systematic treatment, and a new operation called flip, and singularities, terminal singularities. In higher dimensions, although arguments are more difficult, but still we need with these notions, thanks to Birka, Cassini, Haycon, and McCann. And because of this, MMP has become a fundamental tool to study algebraic varieties. So let's review the troubles we had in dimension 3. So I said, starting with a projective variety X, Y can be non-projective. Well, what happens? Well, if Y is non-projective, there is another contraction. So there is some external ray which contracts to another one. So this means you just picked up a wrong contraction. And Y can be non-algebraic. Well, Y remains projective as long as we treat only contraction of external rays. The activities we had. So Hironaka's birational morphism, I will explain in the next slide. Every birational morphism is a composition of differential contractions and flips. And the classification of algebraic varieties without minimal model, the Ithaca program, well, it still works. I mean, it's used by MMP as well. And threefold without smooth minimal model. Well, that's okay. Minimal models can have terminal singularity case. Okay. So this is what we had. And as I said there, P2 contracted to a singular point, C3 modulo plus minus 1. And this is still terminal singularity. And so from here, I pick a curve. I do a flip. After the flip, these surfaces looks like blowing up along a curve, okay? So here, there are two curves, two smooth curves, and each blown up to a divisor. And here, from here to here, it's simply blowing down. Okay, so okay, so I wanted to say something. So right now, minimum model program works in all dimensions, in almost all cases. But if it comes to a concrete description, it's very difficult to describe them if dimension is bigger than 3. So for instance, terminal singularity in dimension 4, it's not classified. But in dimension 3, it's completely classified. So that's why I am still interested in dimension 3, to give a concrete description, to understand the threefold case as explicitly as surface case. You see, my tendency is that if there are big people working on one thing, I try to look at something different. So there are a few kinds. Q-fan threefold. This is treated by Miles 3. He has a database. And Del Pezzo surface fiber bundle, Del Pezzo fiber space. It's done. It's worked on by Hacking and Prohorov. And Q-conic bundle over surface. That's by myself and Prohorov. And divisorial contraction, divisor to point. This is classified by Kawakita. And divisor to curve. Well, at first sight, this may look easier than divisor to point, but it's still not completed yet. So there are various people. And flipping contraction. So it's done. The essential case was done by myself, and I did it while proving the existence. But more, the irreducible case is completely done by Koral and myself, and more general case are still ongoing. Like divisor to curve case and flipping contractions are still ongoing project. Okay, so the underlying are the small contractions, meaning fibers are one-dimensional. So Q-conic bundles over surfaces. Okay, so if X to Z is an extremal contraction of terminal threefold to a surface, then X is terminal, but the Z was not known. The singularity of Z was not known, but we settled that Z has only Duval singularities, or canonical singularities. So it settled Shigefumu's conjecture. So it related to his project on the rationality of rationality criterion of threefold. So since we settled it, I thought he could finish it, but unfortunately he passed away in 2009 before completing it. So it's still ongoing. And divisor to curve contraction. And so if we additionally assume that the bottom, analytic localizing of the bottom at P is factorial, and if C has only analytic branch, then there is extremal divisorial contraction which extracts divisor. So in this case, it's completely classified, but C can have more general structure. Let me let me go to this. So here, I said the three curves very naively, but these three curves can be three branches of one curve. And or it can be one curve and one curve and two branches of another curve. So it gets very complicated. Oops. Yeah. So we have been working on this, and then so general elephant conjecture. The naming is by Miles Reed. So given extremal contraction from a terminal threefold to a jam of analytic space, then there is a Duval member of minus k at p at origin. And the existence of such D is an important step for finding hyperplane section of X through C. Once you have this, you can sort of describe C as deformation space of H. And Prohorov and myself have settled this general elephant conjecture in many cases, and explicit descriptions as well. And it's accepted in the PAM. So, okay, thank you.
Thank you for the description of the great program in minimal model, which is a very fundamental program in algebraic geometry. So let's see whether we have questions. Yeah.
Thank you, Professor. Can you? Yeah. Thank you for great talk, Professor Mori. I asked you two quick yes and no questions. One is about minimal Mara program. Do we have Sarkisov program in dimension 4 and higher? And to some extent, is it completely proved that we have it, or what are the issues?
I think it's ongoing.
Uh-huh.
Yeah.
I see.
You should check with the archive.
I see. And another question is, I was wondering what's the status of realizing steps in the minimal model program as stability conditions and derived categories. Can we think of these different steps as different stability conditions in the derived category of the variety?
I think there are people working on it, and I'm concentrating on describing each step, and so that it can be used by people to describe the whole. Yeah. Right now, it's not completed yet.
Okay.
Other questions? Students? Okay, if not, let's thank you for the great lecture.